How are you? So this is the process of connecting the fan together with an LCD. In this case, I will be using a motor. So the motor will be connected in such a way that it actually represents the fan. In which case, if you have a lower speed, it will be able to indicate on the LCD. That way, you can actually be able to tell that the fan has got a problem. Maybe something like dust has gotten onto it, and it won't be able to work properly. So this should be able to give a warning so that you can be able to open your computer. You know how to do it, so that you can actually be able to repair it. So in this case, I will be using the potentiometer as my input, because the potentiometer will be able to give us an analog value. From that analog value, we basically have it introduced onto the motor, in which case if you reduce the value of the motor, or the output, not the value of the motor, but the value of the potentiometer, the motor speed will reduce. This will be modeling a situation where the dust is being introduced onto the motor, and that way making it not to rotate properly. So I'll be able to connect the devices together, in which case I've talked about a motor which will be representing the fan that will be rotating. Then we have the potentiometer, which will be modeling the dust that's getting onto the motor to reduce the speed, because the moment you rotate the potentiometer and the value is low, then the speed of the motor will also reduce, and that way it will actually be able to give you a warning. So the other thing that I will be able to connect is the LCD, but then the motor is also connected together with a transistor from the digital pin to be able to control it in analog form based on the PWM, that is the pulse width modulation concept. So let me start the connection, and I'm going to use I will use the Arduino. Then my devices will be connected on a breadboard. I'll pick the motor. So this is our DC motor. And then we have a transistor. I'll use the NPN type of transistor. I can connect somewhere here. And then I'll also pick the potentiometer. This one I can place it down here. And then we pick the LCD also for display purposes. So the 16:2 will be able to work without any problem. So you also pick the resistor, which will of course connect the LED, the LCD LED cathode to the ground. That's what I've done here. So this resistor is usually 220 ohms. So you change it to 220 ohms. Then now you start your connections. Of course, we can start with the LCD, which has got the ground, which you need to connect to the ground, though we are going to actually have power on that from down here. Then you have it as ground, black. Then the power connected to 5 volts. Then you have it red. Then the contrast, because you're not going to change the contrast, you connect it to ground. And you have it black. And then the register select. This one will go to pin 2 of the Arduino board. Then the read write will go to ground. So we also ground this. And then the enable, we connect it to pin 3 of the Arduino. We also connect the other pins. Now we actually pick D4 all the way to D7 connected to the Arduino board. So I'll pick pin 4, D4. I connect it to 4, to the digital 4. And then I also pick D5. I connect it to digital 5, the Arduino board. Then we have D6 connected to 6 to port 6 of the Arduino board. I also pick D7. I connect it to 7 as well to the Arduino board. Then, of course, the LED anode, of course, this is the LED of the LCD, will be connected to 5 volts, and we have it as red. So the connection for the LCD is complete. Now we need to connect to the other devices, and I will start with the potentiometer, where I will actually be able to pick the wiper. I think to make it easier, we can move this way so that we can be able to access all the pins. So the first terminal, terminal 1, will be connected to ground. You have it black. Terminal 2 will be connected to 5 volts. Then we have it red. The wiper will be connected to the A0 input. That's the analog input. A0. And we are done with the potentiometer connection as well. Then now we need to connect the transistor and our, so we have, of course, the transistor together with the DC motor. This is how we are supposed to connect. The collector is supposed to go to the negative, like that. The negative, that is terminal 1 of the DC motor. And then the emitter goes to ground. So we connect it down near ground, and we have it as black. Then the positive terminal of the motor goes to the ground, not the ground, but 5 volts there. So we have it as red. Then now, the base of the transistor is supposed to go to one of the PWM ports, and we can pick 9. So we connect it to 9 like this. That's what will be controlling the motor to be able to operate properly. Then we have the ground connected, of course, to the ground of our in the breadboard. You can have it here. You can have it black. Then I'll pick 5 volts, which I connect to the positive section of the breadboard as well. And I'll have its color as red. Then from here, I can tap the negative so that it goes to the upper section of the breadboard. I'll have it as black, like this. Then I need also to do the same to the positive. That is basically 5 volts. I also take it here and connect it to the positive part of the breadboard. Then I also change the color to red. And I think by connecting, there's no any other connection, I believe, which is left. Those are all the connections. You realize that we are using pin 9 and A0 for the other devices. That is the motor and the potentiometer. Then, of course, you're using 2 to 7 for the LCD. So when you're done with the connection, that's the Arduino implementation of your project. You go to the code, which means you are doing now the software control of this project. And we need to go to the interface to allow us to do the code. So here we input, we declare, of course, we can start with declaring the LCD, and we use include. Of course, we start with hash, then include, and we have those 2 signs. Inside, you can put liquid, crystal, so that you're able to get the library. And then we have H. So the next line will also contain the liquid crystal. So I'll just put it there, and then space, then LCD. And I have my pins, which have been used, which are actually 2, 3, 4, 5, 6, 7. So those are these pins that we have actually used for the LCD so that you can be able to display without any problem. So we can also declare, initialize the LCD, and that is how you do it. You will actually do LCD dot begin, because in this case you need to be able to initialize as well so that you can be able to display the values that you are going to give it. So it's 16.2, representing the 16 columns and 2 rows that we have, which it actually which it displays for us those characters that we'll be putting there. And then we can declare the pins, that is 9 and also A0. So 9 is basically an output and A0 will be input. So we have pin mode. Then here we have A0 and we have this as input. So we have basically declared all the pins that are required to be declared here. And the next section will be the loop, where you want to put anything that will be taking place many times. So this is crystal. So as long as this device will be powered, anything that we have inside the loop can actually be able to run continuously, but this one will run just once under setup. So what we put here, first I think we can put the LCD to make sure that it's basically displaying, then we can introduce the other parameters which we require in the control of the motor. So we'll do a printout, or maybe we just do, we read the value from the potentiometer. Let's do that first. So A is equals to, int A is equals to analog read, because that's our input, analog input, and it's connected to A0, so we need to put port A0, and after that we can actually be able to display that value. We see whether it is basically working. So we set the cursor first on the LCD, so we say LCD dot set the cursor. You can check the syntax. C is actually capital. You can see this one, read also capital. M is capital for the pin mode. And of course, the output input, both of them are capital or in caps, upper letters. So LCD.set cursor, and we can do it from 0, 0. So 0, 0, which means it will be printing at starting from the first row, and of course the first column. That is the first pixel. Because here in total we're having 16 pixels and 16, that will give us 32 pixels, which will enable us to display those characters. So then we can do serial dot, not serial, but LCD, because we are dealing with LCD, not the serial monitor, dot print, and we have that in brackets. We can actually do A, so that we confirm it's able to print that before we introduce anything else. So we can test to see whether the LCD is working. So yeah, it's actually displaying the values. So you can see they change from 0 to 1023, which is usually the value we get for our analog input. So it's indicating some digital values there, but it's okay. So let's introduce now the motor, and you also print the values correctly now. So usually the smallest value that we can display for the motor in terms of revolutions per minute is 0, and the highest will be 99.82, as we'll be able to realize the moment you actually turn this to 1023. If you introduce it here, it will actually change this value of rotation to 99.82. So we can actually map that value. And how do we map it? We do int b is equals to, we map comma 0, 1023. Then we have 0, 982, because that's the highest value of the rotation of this motor in terms of revolutions per minute. And of course, the input will be from the potentiometer, which is usually from 0 to 1023 as the maximum value. So what do we do with this value? We can apply let us apply this value onto the motor. So we do analog write. Nine, because our pin control the motor will be actually 9 PWM. As you can be able to see here, they usually have a symbol representing that they are basically PWM. That's 3, 5, 6, 9, 10, 11. But now we only left with 9, 10, 11. And I actually picked 9. You could pick any of these 3. So 10 and 11 could also be picked, no problem. But now we picked 9. So that's why we are going to apply this value, and we'll apply value A to that. So as we apply that value, we can actually be able to print them out on the LCD, and we can use an if statement. So if B is less than 4,000, and B is greater than 2,000. So the range of between 2,000 and 4,000, I want the display to be that your speed is low. The fan speed is actually low. Though first of all, we could actually print the value of the fan. So let's just print it on the serial monitor. And I'll just copy this. Then I put it here so that you can be able to see what value it is. And we will actually be able to print it this way, that we have here, we'll be able to print B. Then just above that, we will be able to change accordingly. So we'll indicate that we are printing the fan speed. So fan speed is, we can just do equals. So fan speed is equals to And then because that will start from 0, 0. Because we wanted to leave a value like 4 pixels on this side, we'll be able to start maybe from 12 to print the other one, the next one. So you can put here 12. And then we print B. So that's before we do any of these statements of the if. Maybe I can actually remove them to confirm that it's printing for us the value be on the screen and correctly. So we run that. So you can see the fan speed is given by 9982. So if I try to reduce this value here, you also see the speed will be reducing because you have mapped. So we need to clear the window. Let's just continue, but we are able to see that it's basically displaying for us something. So we do the if statement here. We say if B is less than 4,000 and greater than 2,000, then we print in the second row. So that's what I changed to 1 there. And I actually indicate here the speed is slow. So speed is slow. So this has not gone up to a point where it can give a warning. Though it shows that actually there is something that is happening already. If we continue, then we are going to have else if. So I'll pick this one. Copy paste it here. From here, what I require is this, so we need to be putting them in the brackets. Then the else if the same. And for this case, I will have it as less 2,000. So this one I'll change it to 2,000. I remove this. Because the moment now it gets less than 2,000, that will be critical. And we can say speed is too low. We count, we can be able to see whether it can actually print this 1, 2, 3, 4, 5, 6, 7, 8. It can fit. That is 16 of these which are actually okay. So then the last one will be else. You don't print anything because now that will be above 4,000 or from 4,000. Then we can do the else. And here we don't print anything. Like that. So we can run to see whether it will be able to work. But usually you need to do a delay, and then you also clear the window. You clear the screen as well. So a delay of 2 seconds is okay. And then LCD dot clear. So let's check what we have for this. So the fan speed is constant for the display. I need to check where the problem is. So please note that the map function we did here is not correct. So we usually put map outside. So then inside we put A. You can see that now because the speed is actually 0, and we had indicated here if the speed is less than 2000, then print speed is too low. In fact, which means that your fan is almost stopping, and therefore your computer might stop running anytime. In fact, in some cases, it's done in such a way that the computer cannot even continue to go to Windows if it realizes that the speed is too low, and you've actually just opened it. So if we change that value to around 2000, as you can see there, this is between 2000 and 4000, and you can be able to see the speed is low. So it's giving a warning so that you can be able to check. In most cases, when it gets here, you can actually have it in such a way that you start now looking at your fan to see whether there is an issue with it. Then when it goes above, it is normal. From 4000 onwards, I think that's okay, we can get. It depends on what is your point of reference. You can actually be able to change those values accordingly. This will be the maximum as I indicated, which is 9982, as you can see there. And it also displays 9982 here. But as you realize, those values are not corresponding. It's because the relation here is not linear for the motor. That's why you realize like now it will be showing 4986, but here it's not. Yeah, so it reduces. So there's no linear relation. You can check on the motor, check properly and see what are the ranges, the actual motor, because this is just a simulation. Then from there you can actually decide on how to map those values from this if you are simulating. But of course, if it's an actual case, you can also be able to tell. Actually, this is what is done usually with development of computers. You first of all do a simulation, then from there you actually do an actual implementation of the same. So this will be a warning system in case you have a problem with a motor, the fan is not rotating properly, because most probably it has a lot of dust. This is what will happen, and you can actually be able to warn somebody. If you want to implement it in terms of IoT, then you actually supposed to connect this device wherever maybe you have a control, this one, and then of course you'll be having a receiver here, wireless most probably receiver, to receive data from the actual device that you're talking about. If it's a computer, from the actual computer. You can either receive that wirelessly or you can have it wired, because Sometimes our computers can also be wired through the Ethernet, but currently most of them are wirelessly connected. So you have maybe a Bluetooth connection, Wi-Fi connection. Like this one, of late we are connecting to the internet through the Wi-Fi, but you could also actually be using the GSM module, which can be connected here. And also on the actual device, which is our computer that you're using, you can have a way that you can incorporate the GSM module so that you can actually get the communication. So you can be able to see it's working. That's how we are supposed to connect it. So speed is too low. Fan speed is 400. Then speed is low. That is relative and not so low. When it goes beyond 4,000, then things are okay, and your computer will just be working properly. So this is one way that you can actually be able to do preventive maintenance to a system. It doesn't have to be a computer. Most digital systems which would be using, of course, power, and in which case we expect, okay, it has some protection. Maybe you're talking about a fan, there's a processor somewhere involved. In case you have a lot of dust, or it happens that actually some object gets uh, into the location where you have the fan, and it blocks it from rotating properly, then you also experience the same problem, and it can actually be able to connect, or it can be able to inform you earlier before the system breaks down. We can call that preventive maintenance or predictive maintenance, because you can also talk about a prediction. This actually, it's like it predicts for you that something wrong is going to happen to your um, computer or your system, so you need to do something about it. So most probably I can label the sections that you are having here, and this will be the LCD display. Then, of course, this is the motor representing the fan. You can put it somewhere here. The motor fan, or the fan motor. Actually, this is the motor onto which you'll be able to connect your fan. And these are transistor. This is the potentiometer. Of course, we assume that it's basically simulating the dust. So port simulating dust. So potentiometer simulating accumulation of dust. So you have more accumulation, then this will be reducing. And of course, that's what we are introducing on the motor, so that the speed reduces. And of course, this is your transistor as we indicated. This one you can be able to put it here, transistor. So this is the transistor I'm talking about here. And this is the potentiometer. And then we have the LCD here. Then up there, we have the fan motor. So that's the experiment. So thank you for listening to me. We can be able to do more projects which are similar for preventive maintenance, because there are quite a number of them. Because that predictive maintenance. Thank you. Bye.